Right, we are going, today is 30th of November 2024. We will talk about symmetric metrics and quadratic form and orthogonally diagonalized. First, symmetric metrics. And by a matrix A is orthogonally diagonalizable if and only if A is symmetric matrix. Symmetric matrix is starting point of orthogonally diagonalizable. What the symmetric matrix has is A transpose and A is same. This is very good property. So then two eigenvectors from different eigenspace are orthogonal. If we diagonalize this vector, then first with eigenvalue, we can find eigenvector, but eigenvector will be not diagonalized. Then we can use x2 or x1 and using Gram-Schmidt formula, take one as v1 and take another as x2. So we can orthogonally project it to, in this case, v1. Then we can find z2. So we can get some value. If we, before solving the problem, if we consider the expected output format, it should be PDP minus 1 format because it should be orthogonally diagonalizable. But in this case, it's 3 by 3 matrix. P inverse will be. So the problem will have definitely PDP transpose format, especially if matrix D is orthonormal. So we can make matrix D as orthonormal by divided by length. Normalize it. So when A is PDP minus 1, able to factorize it, where P is orthonormal and where D is diagonal, then we say A is orthogonally diagonalizable. If not D is not diagonalizable, if not diagonalized matrix, then we should see it. And there's another interesting thing is when A is PDP minus 1, then you can, like doing a scalar root, it can be splitted, then it will be P root P multiply square root D matrix, square root D transpose matrix, and P is transpose matrix. Then we can rewrite it like this. Then we can actually easily solve over. And this is same method with Cholesky decomposition. This is a little different theme, but before go to next theme, if we briefly talk about this theme, we can think about geometric picture of AX equals to B. When it is consistent, then B is in column space A, and related theorem is, if you see the page 341, let U1 to UP be an orthogonal basis for subspace W of Rn, then for each Y in subspace W, it will be represented as linear combination of each orthogonal basis, and especially for weight will be present as Uj dot product Uj each other and Y dot Uj. We can derive it. We can also, I will do next time. And also, if not, then we should do orthogonally project it. We can use zeta to how much the difference is. When zeta is equal to 0, then it is this case. So all points on the line are exactly on the line. In statistic picture, it will be this. How does it relate? That's something. This is statistics picture. and this is linear algebra picture. And when theta is 90 degree, then AX hat and B are independent, and beta is 0, which is in this case. Usually, when theta is smaller, the more linear regression will get better performance. And usually, we use R square in statistics. It is actually cosine theta. We can reduce it by actually B hat square equals to length of BS square equals to length of AX hat square plus B minus AX square plus 2AX hat length of AX length multiply length of B minus AX multiply cosine theta. We'll induce it next time. And back to orthogonal, the diagonalizable concept. In chapter 8, it is quadratic format and definite matrix. You can feel difficult because there comes polynomial is come out. But actually there's very big relationship between definite matrix and polynomials sign. So polynomial sign. Sign will be keyword. So if you see this, positive definite is defined by symmetric matrix and positive eigenvalue. And if matrix is positive definite, then it's orthogonally diagonal. It's able to orthogonal. We can perform orthogonal diagonalization. This is what orthogonal diagonalization is. Then we will see what is positive definite. If A is positive definite, then with arbitrary vector x and x transpose, and A will be some numbers, then it will be bigger than 0. In positive semi-definite, then it will be bigger or same than 0. And if it is negative definite, then it will be smaller than 0. And if it is negative semi-definite, then it will be smaller or same than 0. So positive matrix is related with quadratic form. The second order polynomial sign, so it is deeply related. So in this case, the matrix A eigenvalue are all positive, and it is symmetric matrix. Then the quadratic form will be also positive. You can also prove it by the formula, which is x transpose AX will be, you can write it like this. In this case, A is currently decomposed right now. We can write Y, which is U1 matrix U and matrix X's multiplication. Then we can rewrite it as Y transpose Y with eigenvalue matrix. In this case, then it will be lambda 1 y squared plus lambda 2 y squared plus lambda 3 y 3 squares, which can we can show eigenvalue directly here. So we can easily prove it. So this was the summary today. I will see you next time. Thank you.